Okay, so this is the next video in the additional maths series and the subject today is vectors, and I've called it Vectors Basics because we're going to look at exam questions that use knowledge that's mostly already in P1. So P1 of course being part of the AS Maths course. And so what kind of knowledge should you already have about vectors from P1 or maybe even earlier in your school career? You should already know firstly how to add and subtract vectors, and that means knowing the idea of a diagram like a triangle or a parallelogram. So vectors such as u and v can be added using a parallelogram, something like that. You should be familiar with that idea. So that's addition and subtraction. What else should you know? You should know how to represent vectors, or how to write them as displacement vectors. If it's a vector from one point A to another point B, it could be written in this way. If it's a position vector, then it's the vector from the origin to the point A. So the vector OA, the displacement vector OA, is usually referred to as a position vector, and it's usually written with a lowercase letter. So this is a lowercase a with an underline, and that's how I would expect a student to write it on paper. Then there's unit vectors. This is something that students don't immediately understand, I find, so I hope you've studied it already. A unit vector is marked with a little hat, or a quite sure how else to describe that, an upside down V above the letter, and it's defined as being the vector divided by its own length. So here it's being divided by a scalar number, which is its own length, which brings us on to the next point. You should know the idea of scalar multiple, so that if we have a vector A, it can be multiplied by a scalar such as the number 2. This would be 2A. So k times a, where k is a real number, is a scalar multiple of a, and it's parallel to a. Looking at this picture, you can see that 2a is parallel to a, it points in the same direction, but it's twice as long. And k can be 0, giving us a 0 vector, or k can be negative. If k is negative, then we get a vector pointing in the other direction. And the last point I wanted to mention is parallel. What are the conditions for two vectors to be parallel? Two vectors u and v are parallel under what condition? Do you know? Well, the answer is best expressed by saying u is equal to kv, where k is some real number. That tells you, in fact it's both ways implication, that u is parallel to v. But the important condition on that is you should understand that if k is negative, let's put this in brackets, if k is less than 0, we sometimes call this anti-parallel because the vectors point in opposite directions. So here the word or the prefix anti, meaning opposite. So the vectors may be anti-parallel, but actually most of the time, even if a vector is anti-parallel, it's still considered to be parallel because the lines of the two vectors are parallel to each other, or the line segments. Okay, you may have noticed I missed something, but that was deliberate. I missed dot product. Dot product is not required in additional maths. So dot product is sometimes called scalar product, and that refers to the formula a dot b equal to modulus a modulus b cosine theta. So that formula is not required, and it's not used in additional maths. Okay, so that's fine. You should know that stuff. If any of the things I just described you've never learnt before, well, you'll have to do some reading. In fact, there's something wrong, because you probably shouldn't be doing this course in that case. But nevertheless, that knowledge is explained briefly in the textbook that you have. okay, now let's come on to my next point. Now this is a bit of a strange description I want to give you, but bear with me. It's worth thinking about this before you start doing the examples in the textbook. And it's the idea of actually I'm not sure of the right word to use to describe this. I suppose I can use this name, which is a bit technical, and you certainly won't see this name written in your textbooks, but I may as well explain it to you. So non-orthogonal coordinate systems. Now here the word orthogonal is something you won't see in textbooks until you get up to maybe the further maths level, so just before you're getting into university, and indeed if you study maths at university, the word orthogonal will be quite important, or even physics and other sciences. So orthogonal is closely connected, so the idea of orthogonal, let's say, is similar to the idea of perpendicular. So it's like the idea of perpendicular, and what you should remember from P1 is that perpendicular itself is closely connected to the dot product, and the dot product being 0 means that the two vectors are perpendicular. And it's a neat thing to know because it works in any number of dimensions, not just on a two-dimensional surface, but also in 3 dimensions or even more. Although we can't visualize that, it's still a useful idea. So we say A and B are perpendicular if they have nothing in common in their in their direction. They don't affect each other, is another way to think about it. Now if that's true, of course, then we're looking at a picture like this. Perhaps B is pointing upwards and A is horizontal. So this all sort of goes together. But now you'll see that the diagrams that I've already drawn, so this diagram here and this diagram that I copied from the internet, don't look like that. So if you imagine, let me draw using a different color, look at these vectors here. If you imagine that these vectors are mapped onto a grid, so grid here is a bit like a graph, but not the same. Imagine this is the origin, and imagine that A is pointing that way and B is pointing along this way. Now if we choose, so again, imagine this is a grid. Imagine you had a strange piece of graph paper. Usually graph paper has grids like this, yeah? Usually graph paper looks like this, lots of vertical lines, lots of horizontal lines. But imagine it looked like this, or imagine that the graph paper was on a piece of rubber, a rubber sheet, an elastic sheet, and you stretched it. So you stretched it to the left while holding the up and down the same. You'd see this effect where the grid changed its shape, yeah? So instead of here we're seeing rectangles or squares maybe, here we're seeing parallelograms. Parallelogram, parallelogram. Now I've drawn this very roughly, but you can see a more accurate example in this diagram here of the same thing. But so to come back to my original point was, imagine we just took a particular point on this stretched graph paper or this stretched grid, and we asked ourselves, well, how could we identify the position vector of this point? Well, the position vector is the vector from the origin to the point. Let's call this point P. So what's OP? Well, we can clearly count the number of A and B's needed to get there. If I go to the right, I see 1B, 2B, 3B here. So the position vector of this point is 3B, assuming these are all equal. And how many A's do we need to get from here to P? Well, we clearly need 2 A's, don't we? And so we can assign coordinates to P, 3, 2, meaning OP is equal to 3B plus 2 A, like that. Now, this of course is exactly what we do usually on an ordinary graph when we write coordinates of a point. We count how many I and j vectors we need to get to that point. So on an ordinary graph we count the number of squares or units we need to go to the right. That would be the number of I vectors we need, and then we count the number of j vectors we need, and we assign the numbers 3, 2 or whatever it happens to be to that point on that basis. Now of course this way of counting is unique, and you might like to think to yourself, how can I prove that there's only one point P that has 3 B vectors and 2 A vectors? Yeah. Obviously you can reach it in a different order. You can go 1, 2A, 1, 2, 3B. But there's clearly only one point that has that property. Now, what do we need? What needs to be true about A and B so that we can make this kind of picture, like the picture on the right here? I can just choose some random point on the graph. I'll use a red color maybe. And I won't even put a point on the grid. I'll just put a point randomly there. Now I know that there's a unique number of these vectors and a unique number of these vectors that will get me to that point. So that if I have two unknown vectors u and v, and if I know they're the same vector, then I know that if I express u in terms of these two vectors, again let's call them b here and a here. So if I know that if u is 3a plus 2b, sorry, what am I talking about? That's obviously not 3a and 2b, but I'll make up some numbers. I won't actually count them. Suppose u is 17a and 18b. It follows that v must also be 17a plus 18b. Now again, let me come back to this question. Will that always be true? Here we saw that we don't need this. Look at this. We don't need orthogonal. We don't need a and b to have a dot product of 0 for this to be true. Okay, I realise this is a bit difficult to follow, so I want to draw another picture. Maybe coming back to the more basic case will help us understand better. The more basic case is where, just need that one. Come here. No, it's not working. Okay, let's try this again. What I'm doing here at the moment, sorry it's taking so long, but I'm drawing a normal IJ type graph, or trying to. In other words, a normal XY type graph. Let's draw ourselves an x-axis. Okay, that's better. Now, I want to go back to basics so you can see that what we're talking about still is really something very similar to a normal graph. Because on a normal graph we can imagine one unit of x is I. Now that vector has size 1, and then we have a vector j which also has size 1 pointing vertically, and I dot j is 0. But what I'm trying to explain here is that is not necessary. We can, if the graph paper is stretched, if the directions of these two vectors are different, if the directions of these two vectors are not perpendicular, the same idea of using coordinates, of using fixed combinations of the two vectors still works. So coming back to this case, if we had a point here P whose coordinates were, let's say, 7x and 2y, there is no other point on the plane which has 7x and 2y, plus 7x and plus 2y. And that's obviously still true in the cases that I've drawn here. So will this always work for any vectors a and b? Here we're observing that the dot product of a and b doesn't have to be 0. Here a dot b is not 0. A dot b is not 0. Yeah. So maybe the diagram is confusing now because that's pointing to a dot b equals 0. But in this case a and b do not have 0 dot product. And so we'll see that it always works as long as a and b are not parallel. That's the only rule we have to obey. If a were parallel to b, then we would be drawing two vectors here, b and then another vector a, and what we would be getting is just mapping along one line. We would find positions along one line only. We could never get to this point up here by a combination of two vectors which point along the same line. So the condition is only that a and b should not be parallel. If a and b are parallel, it's not possible to make a coordinate system in 2 dimensions. But so we are allowed to use a non-orthogonal coordinate system, by which we mean a coordinate system where the two vectors are not orthogonal, which means not perpendicular. It still works as long as the two vectors are not parallel. And although all this probably seems very sort of strange, why is he talking about this? The reason it's important is precisely because of what I wrote in red here. Yeah? If two vectors are the same, then they must have the same linear combination. The 17 and 18. They must have the same linear combination of a and b. So this, just like when we studied identities with polynomials, the fact that two vectors are the same in 2 dimensions is really 2 equations, not 1. It looks like one equation, u is equal to v, one equation. It's not. It's 2 equations if we're working in 2 dimensions. For example, look at the column vector 3, 7. 3i plus 7j. And look at the column vector a, b. Well, this tells me that a is 3 and b is 7. Yeah? So that's something you've probably already used many times. But you notice one vector equation is 2 scalar equations there. You should remember this principle, and what I'm trying to tell you is that that principle still works even if we're not using ij to map a point, but we're using some non-orthogonal coordinate system. Okay, because that idea is quite difficult to understand, I'm going to immediately show a question which partly uses the idea. To be honest, I'm not sure if we actually really have to use that idea, but it's often very useful to use that idea. So anyway, here's an exam question. Now there aren't many very difficult exam questions on vectors apart from the topic of relative velocity, which I'll cover in the next video. But there are a few questions, and it's good to have the right the right methods. So let's look at this question here. We have first a diagram. That's always useful, of course. So here's our diagram. We have an origin, O, and we have the position vectors of P and Q written as lowercase bold letters P and Q. So when you're writing this on paper, you should underline it, yeah? P and Q. So in the diagram, OP is P, OQ is Q, PM is 1/3 PQ. So we already know that this displacement vector from P to M there is 1/3 of the displacement vector from P to Q. Well, that means MQ is twice as big as PM. And ON is 2/5 of OQ, so these two lines are in the ratio 3 to 2. Okay, now let's actually answer the question, best we can anyway. Given that OX is MOM, express OX in terms of M, P and Q. So notice here they're not asking you to find the position of X. They're saying, let's just give a number, M here, lowercase m. That's a scalar number. well, this is rather a variable, and we're going to write an expression for OX using that variable. Okay, so to get from O to X in terms of P and Q, how do we do that? Well, first of all, we can go from hold on, where am I going here? From given that OX is MOM, right? So OX is OP plus oh, I see, sorry, I misunderstood. Right, so what we should do is find an expression first of all for OM. So let me write it here. OM, well, that's OP plus PM. And OP is P, and PM is 1/3 of PQ. So that's 1/3 of PQ. That's an underline there. Now PQ, of course, by simple vector subtraction, PQ is OQ minus OP. So it's 1/3 of Q minus P. And lastly, we're going to observe that to get OX we need to multiply OM by M. So this is following down into here. So what am I doing? OX, so therefore OX is little m, that's a scalar multiple, times OM, which is P, plus 1/3 of Q minus P. Now let's just tidy this up because it's a bit messy. So it's m over 3Q plus, how many P do we have? 2/3, plus 2m over 3 P. So that is an expression for OX in terms of M, P and Q. So that was part 1. So let's have a look at part 2. Part 2 asks something very similar. It says given that PX is NPN, express OX in terms of NP and Q. So PX here, let's maybe use another colour. So PX, this thing here, is N times PN. So what we probably need to do is get an expression for Pn and then multiply it by this new scalar quantity, or this scalar variable N. This is a bit difficult to say in English, isn't it, because there's so many upper and lower case letters. I hope you can follow. So let's think about the vector, displacement vector from P to N. How do we write that? So P to N would be from O to N minus from O to P. So let's do that first. Pn, according to vector subtraction, is On minus OP. Now On, according to the original information, On is 2/5 of OQ. So we'll replace that with 2/5 OQ minus OP. So that's 2/5 of Q minus P, where here Q and P are the position vectors of Q and P. Now we're going to multiply Pn by little n to get Px. So Px is little n times Pn, which is 2/5 of Q minus P. So that's it. We'll just simplify that a little bit. 2n over 5 Q minus NP. So that's an expression for Px. I'm sorry, what am I saying? Px is okay. Okay, so that's px, but the question is actually asking for ox. So to get ox from px, I need to add p, don't I? So therefore ox, let's just make a bit more room here. So therefore, what are we saying? Ox is, of course, now this is simple vector addition, is op plus px. Hope you can read that. So that's p, the position vector p, plus the expression we just wrote, 2n over 5 position vector of q minus n times the position vector of p. So tidying that up, I'm getting 2n over 5 q plus 1 minus n p. Okay, so they made us do some algebra, basically what you could call that vector algebra, but every step is based on the idea of the simple vector sum. For example, when you want ox, you can do op and then add px. Just like a journey, you can go from o to p and then from p to x. It gets you to the same place as if you went from o to x. Or something more complicated like OQMX. So OQ plus QM plus MX gives you the same as OX. And that's something you should have learned already. But here's of course the point of the question, part 3, hence evaluate M and N. So do you see what they're doing is they're saying that given that we know the position of N and M on these two lines, we can find the position of X using a vector method. Because by writing the position of X, in other words the position vector OX, in two different ways, we get different expressions for the same vector. And then we're going to use the principle that we saw up here, I think, in order to find the values of those scalar constants M and N, which gives us the position. So I suppose I'll do it here. So it says hence evaluate M and N. So we must use what we already know. So let me underline hence. Let's use what we already know. So we have two expressions. There they are. Let's underline them. The first expression was OX is this. The second expression was OX is this. So let's equate those two. Let me select and copy. I have this. Excuse me. So I have this one. This was our first expression for OX, and it must be equal to our second expression for OX, which was this one here. Yeah, so they're both equal to OX. Now we use the idea that I've just described at the beginning, non-orthogonal coordinates, because we have the same point. Let's look at the diagram again. You see that these vectors OP and OQ are just like the pairs of vectors that we saw in these diagrams. They're not orthogonal, they're not perpendicular, but they map out a coordinate system in 2 dimensions. So there's a fixed number of P and Q that will get you to X from O. So I can equate the coefficients of P and Q to get the answer. So let's look at P, for example. We have 2m over 3 on the left hand side, and we have 1 minus n on the right hand side. So that's our first equation, and we have m over 3 looking at q. So let's put the origin of this. This is for P, and for Q we have m over 3 on the left hand side, and on the right hand side we have 2n over 5. That's equation 2. So let's combine the equations. It's not too difficult, is it? Twice that, so doesn't really matter. Divide the let's divide 1 by 2. That's as good as anything else. On the left hand side we'll have 2m over 3 over m over 3 is 2, and on the right hand side we have 1 minus n over 2n over 5. So I'm getting 4n over 5 equals 1 minus n. So I'm getting, what's that, 9n over 5 equals 1, I think. Looks right, yep. So n is 5 over 9, and m, what's m? M is 6. 6 over 9, m is 2 over 3, I think. Okay, I may have made a slight error in the numbers there, but it doesn't really matter if I did or didn't. The method is clear enough, I hope. So the key step here, in a way, I mean, the first part of the question, you should find that quite easy if you understand how to add and subtract vectors. If you haven't had much practice with that kind of process, you should definitely practice it with examples from the book. But the reason I'm showing you this example is this step at the end, because you may not be completely comfortable with that step unless you've actually thought about the idea of non-orthogonal coordinate systems. Now, you may not have called it that, but that idea is important. Anyway, I'm not going to go through lots of other silly little examples, like I've got little questions here about unit vectors, because you should know that already. So let's leave that alone. In the next video I'm going to talk about the rather difficult topic of relative velocity. So thanks very much.